Welcome to the Deep Dive. We're the show that, well, cuts through the noise to get you straight to the knowledge that matters. And today, we're jumping into one of the most exciting fields out there, renewable energy. Seriously, the pace of change in solar, wind, storage, it's just incredible. And our mission for this deep dive, we're going to unpack a really interesting U.S. patent. It's not just about the tech, which is groundbreaking, but also about how fast it got approved, which, believe me, is unusual in the patent world. We're talking about a new solar technology from a company called Tongwei Solar. We'll dig into what it is, why it matters, and what its speedy journey might tell us.
That's right. And the company behind it is Tongwei Solar, Jingnukao Ltd. They're based in Sichuan, China. Now, Tongwei Solar, they're a pretty big deal in the photovoltaic world, a major manufacturer of high-efficiency solar cells. So definitely a significant player pushing solar energy forward globally.
Okay, so a heavyweight in the solar industry. That definitely sets the scene. But what really made us do, a double take here, was the timeline for this specific patent. Can you walk us through those dates?
Absolutely. So we're looking at U.S. patent number 12,369,427B1. It was filed on October 31st, 2024. And here's the kicker. It was granted, fully approved, on July 22nd, 2025.
Okay, hang on. Let me process that. October 24 to July 25, so that's what? Under 9 months?
Just under 9 months, yeah.
9 months for a U.S. patent? That's almost unheard of. I mean, the typical process takes, what, years?
Oh, easily. Several years is common, sometimes 5 years, sometimes even longer. There's a lot of back and forth usually.
Right. So this kind of speed, it feels significant. Does it suggest the innovation was just that clear-cut? Or maybe, a sign that certain technologies, especially green tech, are getting fast-tracked, even from overseas companies?
It's a really good question. And yeah, that speed is fascinating. It could mean a few things. One possibility is that the invention itself was just incredibly well-defined, novel, easy for the examiners to see the value and approve quickly. Clean application, clear breakthrough. Another possibility, as you suggested, is that maybe there's a push, perhaps an implicit one, to streamline the review for critical technologies, things related to energy security or climate goals. And just for context, there was an earlier Chinese patent application filed back in June 2024 that got its first feedback, the first office action in October 2024. So, groundwork was laid. But still, getting the U.S. grant that fast is exceptional. And the inventors credited here are Yang Chen, Jianbin Fan, and Shaji Meng.
Okay, so the speed itself is a story. It definitely hints that this innovation is something special, something that cuts through the usual red tape. But let's get to the core of it. What is this innovation? And maybe more importantly for you listening, how could it actually change solar energy? What problem did they solve?
Right. So fundamentally, this patent tackles a really persistent headache in solar cells. It's about high contact resistance and inefficient current collection.
Okay, break that down a bit. Resistance and current collection.
Think of it like, okay, a solar cell makes electricity from sunlight, right? Like water from a tap. But if the pipes carrying that water away are too narrow, or they're clogged up, you lose pressure, you lose flow. A lot of water gets wasted. Similar with solar cells. If the electrical pathways out of the cell aren't efficient, a chunk of the electricity generated just turns into heat or, simply doesn't get collected properly. It's lost energy. So this patent is about a specific metal-semiconductor contact structure and the method to make it. It's designed to basically unclog those pipes.
Okay. So it's not about generating more electricity initially, but making sure more of the electricity that is generated actually gets out and does useful work. Optimizing the exit ramp, sort of?
Exactly. That's a great way to put it. You optimize that crucial handoff point where the electricity leaves the silicon material of the cell. And the clever bit is how they do it. It involves the main light-absorbing part, the doped silicon-based semiconductor layer, and the metal electrode that carries the current away. Standard stuff so far. But the breakthrough is this unique pit island structure they create within that silicon layer.
A pit island. Okay, that sounds interesting. What does that do?
Inside this tiny pit island, there's something called a conductive aggregate. It's basically a mix of special glass-like material and tiny metal particles.
Wow, that sounds incredibly precise. So this pit island structure with the aggregate, how does that actually help the electricity flow better? Is it creating, like, a shortcut?
Yeah, you could almost think of it like building microscopic superhighways for the electrons. This structure creates much more efficient electrical pathways right at the contact point. It dramatically lowers that resistance we talked about, removes the bottlenecks, and it improves how the current is collected overall. The end result: better electrical performance, higher efficiency for the whole solar cell, less energy wasted.
That's really clever, making sure every bit of captured sunlight counts. So, thinking bigger picture then, where would we see this tech being used? Is it for one specific kind of fancy solar panel, or could it improve lots of different types? The market's pretty diverse now.
That's one of the really strong points here. It's versatility.
Yeah.
The patent makes it clear this isn't just for one niche type of cell. It's applicable to, well, pretty much the main types used today and emerging ones too. That includes standard PERC cells are everywhere, kind of the workhorse of the industry right now. But it also works for newer, higher efficiency designs like HJT cells, that's heterojunction, and Tito-Pecan cells, which are really gaining ground. And even IBC cells, the ones with all the contacts on the back.
So, it could potentially upgrade a huge range of solar panels out there.
Exactly. It has broad applicability, which means it could lead to widespread improvements across the board, not just in one corner of the market. That's potentially a big deal for the whole industry.
Okay, that's a great picture of the what's and the whys.
Yeah.
Super interesting. But, the how is often where the real magic is, especially with something this precise getting improved so fast. Let's maybe peel back one more layer. Can you give us a sense of the engineering details? What makes this pit island thing actually work so well?
Absolutely. And you're right, the precision is key here. We're talking about engineering at the nanoscale, really. So the pit island itself isn't just a random bump. It has very specific features, like it contains multiple tiny holes, and the patent specifies their diameters between 10 and 100 nanometers.
Nanometers, so incredibly tiny.
Oh, yeah, unbelievably small. Like a human hair is tens of thousands of nanometers thick, so these are minuscule. And the total surface area of this pit island structure is designed to be significant, 50 square micrometers or more, to provide a good large area for that electrical contact. The patent also mentions something called a pyramid textured structure on the silicon surface nearby. That's not just random either. It helps trap more light within the cell. More light trapped means more electricity generated. And the materials, the metal electrode can be common stuff like copper, Cu, or silver, Ag, which are great conductors. The special sauce, that conductive aggregate inside the pit island, could be things like a silicon-based eutectic mixture, or maybe a lead-free solder glass materials chosen to form that perfect electrical bridge.
Wow, so it's a combination of nanoscale architecture and carefully chosen materials. Given how incredibly small and precise this all sounds, I'm guessing making these things isn't exactly straightforward. The manufacturing must be pretty sophisticated.
You bet. The preparation method is crucial and involves very careful control. Think of it like high-tech nanoscale sculpting. It involves several steps. There's a pre-sintering phase first, heating things up pretty high, like 700 to 850 degrees Celsius. That sort of prepares the surface and materials. Then comes the really critical part, a laser-induced contact treatment.
Lasers.
Yeah.
Knew they'd be involved somehow.
Right. This isn't just any laser, though. It uses specific settings, a certain voltage applied, specific wavelengths of light, very precise energy levels. This laser step is what actually creates that pit island geometry and embeds the conductive aggregate in the right way. It's incredibly precise work. And finally, there's a post-sintering step, heating it again, but usually at lower temperatures, maybe 100 to 800 Celsius, to kind of lock everything in place and optimize the connections.
Okay, so those steps, the sintering, the specific laser treatment, why are they so vital? It sounds like that's the core of actually making this structure perform, right? Building that electron superhighway you mentioned.
Absolutely. That's the secret sauce, if you will. The pre-sintering sets the stage. But that laser treatment, that's the make or break step. It's what precisely forms those unique pit island structures, gets the conductive stuff exactly where it needs to be, almost like microscopic 3D printing combined with welding. Without that level of precision control using the laser and the specific temperatures, you just wouldn't get the structure right. You wouldn't achieve that ultra-low contact resistance and the improved current collection. The whole efficiency gain depends on getting that nanostructure perfect. It really highlights the advanced engineering involved.
It really does. So as we wrap up this deep dive, looking back at this Tongwei solar patent, what's the biggest takeaway for you, considering both the tech itself and that remarkably fast approval?
For me, it's the clear practical impact this points towards. This isn't just theoretical. Tongwei Solar seems to have found a very tangible way to improve solar cell efficiency by tackling these known problems: resistance, collection with a really novel, detailed structure. It represents a real step forward in getting more power out of solar cells. And that rapid patent grant, it really underlines how clear and potentially important this innovation is perceived to be. It may be hints, like we discussed, at a global recognition that we need to accelerate these kinds of critical green technologies. If this gets widely adopted, it could mean noticeably more power from the same size panel, maybe driving down costs eventually, and just helping us move faster toward clean energy goals.
Yeah, exactly. This patent, approved in what feels like record time, showcasing such precise, almost microscopic innovation. It really makes you think, doesn't it? Are we maybe entering a new phase where truly critical renewable energy tech sees much faster development, faster deployment?
It's just
If the
fascinating.
world and the systems like patent offices start moving faster for these kinds of breakthroughs, what kind of impact could that accelerated innovation have on our whole energy picture in the next few years? It's definitely something interesting to ponder as we look towards a future, hopefully powered by smarter, more efficient energy.